Good afternoon, everybody. My name is Gary Cox. I'm a broadcast engineer with KTXL FOX40 here in Sacramento. I'm pleased to be able to give you a presentation today on broadcast engineering. We're going to talk about, first of all, what that is, and second, what was it, what is it, and what will it be? Because among people who know what it is, a lot of people think they know what it is, and it turns out it's evolved since the time that was what we usually think of when we think of it. So I'm going to start with the very beginning, and the reason I'm doing this is because one is to show you that this is often what we think of when we think of broadcast engineering, but we've moved on from it. But second, it's really important to understand the fundamentals of what broadcast engineering involves, which is at the fundamental, it's electrical engineering and radio waves, and now computers as well, but we'll get to that in a minute. Very beginning of broadcast engineering was the discovery that we could actually transmit information across space. That was a very profound discovery around the turn of the century, late 1800s. And what they found was, we all heard of the telegraph, right? It's when you put electricity across a wire, you run it long distances, and you tap Morse code to get information across. Well, early on, they started to notice that when there was a spark of some sort, whether it was from lightning or it was from static electricity, when it was near the wire, they would hear it on the wire. They said, well, how can that be? There's nothing connecting the spark to the wire. So after a time, they discovered that there was something called radio waves. And so what the very first radio transmitter is this here. It's called a spark gap transmitter. And basically all it was, to greatly simplify it, was you see these two balls right here. There's two balls, we call those electrodes. What they did was they charged up electricity on one, and they charged it up so high that it would spark across to the other one. And when that spark occurred, it would be basically put onto what's called a LC circuit. There's a little, basically allows it to resonate, and then it would go up on an antenna and it would broadcast the spark all over the place. Now this was very rudimentary, and today we have radio and you tune to a particular frequency. This thing actually spewed frequencies all over the place. It was, from 100 megahertz down to 0. And so there was no frequency to tune to. This right here was the very first radio receiver. All it was it actually had right here in this tube were little bits of metal shards. They just put little flakes of metal. And what they found was that when the radio waves would hit this, those little bits of metal would congeal to each other. They would get a little closer, just microscopically get a little bit closer to each other. And that would cause the electricity to flow a little bit more through the metal shards. And then that would ring a bell. So a little circuit that's sensed the electricity going through a little faster, not faster, but with less resistance, so it flowed a little better, we'll say it that way. And so this was the very first radio receiver and the very first transmitter. There was no frequency to tune to anything like that, but that's where we started. This was actually called a coherer. That's actually the name of it, because the metal shards would cohere to each other. From that, around the 1910s and by the 1920s, we had something called vacuum tubes. And some of you have probably heard of that. Probably the most well-known vacuum tube is the light bulb. That one there, that one, not that one, actually none of these are actually fluorescent, but actually fluorescents are tubes as well. But the vacuum tube, basically all it is it's anything where you have glass and you take the air out of it. You either have nothing in it, which is a vacuum, or you might fill it with a noble gas. Any of you in chemistry have heard of a noble gas. It's a gas that does not react with any other gas or any other chemical at all. And then you have electricity, little electrodes that are placed inside it. And what happens is electrons are able to travel through the vacuum in a way that they don't in air. And so we can do a lot of interesting things with vacuum tubes. And in fact, we still work with vacuum tubes today. At FOX40, we still have vacuum tubes that we use to transmit. So this was the very first vacuum tube that was used. There were earlier ones, but this is what really started radio being broadcast. And it is essentially called a triode, and it is essentially the predecessor to the transistor, which really gave us computers, right? That's basically what led to computers, semiconductors, and being able to dope silicon to be able to act a certain way with electrons in certain conditions. Then anyway, basically how it works is there's three called triode, tri being the Greek for three, and ode being the Greek for road, so three roads, literally what the word means. You have a plate or an anode. If you're in chemistry, you may know anode is the positive side of any circuit. And you have the cathode, which is the negative side. The way to remember that is cat. If you don't like cats, cats are negative. Okay, so that's how you remember that if you need it in a test. If you do like cats, just say, you know what, that guy, he was kind of mean, so I'm going to do the opposite of what he said. I like cats, so I'll do the opposite. And then you have the grid. And we still use this fundamentally. This is still how it all works today, and this is fundamentally how transistors work in your computer. Basically, you would put electricity, would flow from the cathode to the anode because electrons flow from negative to positive. Now, we often pretend they flow the other way, and we call that conventional current, but they actually flow that direction. But the grid, this was what really was revolutionary, because what we found was we can put a signal on the grid, a signal like maybe a microphone. Maybe I could be talking into it, and of course you've all seen when you talk into a microphone, that turns into an electrical wave. And if you put that into a speaker, the speaker moves with that particular wave pattern, and you hear the reproduction of the sound. And that was something we discovered earlier with telephone. But we found if we put this signal on the grid, what actually happens is this much higher power we put between the cathode and the plate. You have a lot of electricity flow from the cathode to the plate. This grid acts as kind of like a gate. It's kind of like a gate or a valve. In fact, the British call vacuum tubes valves for this very reason. This essentially acts as a gate, and so what happens is the output of this tube on the anode is actually becomes a humongous copy of this small signal. So if we put a microphone, which is the output of which is very small, if we put it on this grid and if we get a large amount of electricity from the cathode to the plate, the output, it's like a huge copy, and then we call that amplification. And that's what we weren't able to do until the discovery of the vacuum tube. There were a few other things we needed to discover as well before we could do radio transmission. One was being able to put on a particular frequency, something we called modulation. And demodulation is a process of taking it back off that frequency and putting it back down to being able to hear it. If you really are curious how that works, that's called heterodyning. But once we had those two developments, we were able to broadcast for the first time. So modulation allows us to basically take because my voice and your voice and his voice and her voice are all roughly within the same frequency, and they're very low frequencies. They're within roughly 600 to 6,000 hertz, very low. When we talk about radio, of course, you ever tune to radio, you see it says K hertz, kilohertz, or megahertz. That's thousands or millions of hertz. It's much higher than anything we have. And in fact, when we speak, it's not electrical waves, it's actually mechanical waves. We're actually, right now as I speak, I'm actually vibrating the air in this room. And that's how you're able to hear me. Your ears detect the vibrations. Radio waves work a different way. Radio waves can go through space. They can go through anything because they're electromagnetic, meaning they're actually, they're not mechanical. They're actually part of the universe itself. And what we can do with what's called modulation is we literally, the process of, so I didn't want to get into it so much, but since you asked, I'd love to tell you. The process called heterodyning is where we mix. What we have is we have a crystal, and that crystal is, you ever heard of resonant frequency? Did you learn about that? Well, basically, see if I'm knocking on that, you hear there's a particular tone to that. If I knocked on this, right, this is a good example. No, it's not. That's a better example. You hear that particular tone to that, and we're in the music room, it's appropriate. Every object in the universe has a particular frequency at which it naturally makes a particular tone. That desk has a particular tone, resonant frequency to it. And a crystal has we can cut crystals to very particular ways so that their resonant frequency is a very specific frequency. And when we put electricity across it, it basically screams that frequency very loudly. And we will put that frequency at whatever, like let's say you want to listen to 88.9 FM megahertz. So this is an oversimplification, but basically we would have something that would create that frequency, and then we would take your voice and we would mix the two. So essentially we would put your voice and mix it with that high frequency, and so we can transmit that frequency with your voice mixed into it, and then the receiver will actually demix it and take your voice back out down. And that's how we can have different information across different frequencies, and we can use the spectrum. The spectrum is the totality of all the radio waves. We can use it and multiplex. It's called multiplex. It means you're using different parts of it for different purposes. We can layer it so we can transmit many things at once. So that's how it works. It actually mixes frequency, your frequency with a higher one together to transmit. So very good question. Mm-hmm. If you'd like to learn more about that, look up this word here, heterodyning. Heterodyne. You learn about that. This is a very early AM radio transmitter. This was actually in Portland, Oregon. This was at KEX. This was a very powerful transmitter. It was the first high-power transmitter in Oregon, and it actually transmitted so powerfully it went all across the entire west coast of this country. You see it's very large. It's 50,000 watts. That's a lot. Then we have television. Now television is, in its way, it's basically just radio. It's the same thing, except we need a way to take a picture, an image. We have to find a way to turn the image from a camera lens into an electrical signal. Because now we know how to make an electrical signal go across the space. But how do we take something from a camera lens and make that into a signal we can put across? Well, the invention of the cathode ray tube, which is another kind of vacuum tube, is what allowed that to happen. Now, a cathode ray tube, you've all seen that. There's not one in this room. Sign of the times. The old TVs, the ones that aren't thin screens. But basically what they do is they take light, and there's a phosphorus coating on the inside on a little film. They take that light and they take an electron gun. It works a little bit like this laser pointer, but more complicated. And the electrons and the light will interact on the phosphorus. It's a chemical reaction of sorts. And that causes the electricity to come in, and then we can actually, that's what we put in the camera. Now, we actually use these tubes in cameras up through the 1980s. And we use them in the reverse sense to project the screen up through, well, just a few years ago. And they were really quite marvelous bits of technology lasting that long. This is a very, very early television studio. This is 1937 in NBC. You can see how big these cameras are. These had what were called ionoscopes in them. They're very early vacuum tubes used to convert light from a camera into electricity. And once we have an electrical form, it's fairly simple to just transmit it. Now we know how to do that. This is really cool. This is an early cathode ray tube. This is how we turn light into electricity. This is a picture of one. This is a diagram, and this actually is a really cool early picture from our magazine RCA put out, promotional, basically advertising this new-fangled television thing. And what they have is, this is inside, you see this glass case here, this is all vacuum in there. And this is the electron gun. Electron gun. All cathode ray tubes have an electron gun in them. And this is artistically, an artist inserted this airbrushing showing the electrons spewing out. It doesn't actually, you don't actually see that. But they'd come out, and basically it would scan across the image. It would scan across it. And as it scanned across, the electrons touched the phosphor, and then if at this particular moment, see, this is where her hair is, so it's darker, the electrons would not react as much with the phosphorus, and it would cause the electricity not to come out as much as if it were on the lighter part of the image. And then that would how we have basically an electrical signal from the image. So that's how that works. And we have, of course, early televisions with cathode ray tubes. This is what it looks like from the side, at least an early one. Later on, they got a lot narrower. They weren't that long. But basically, everything looks like it moves, but they're not really moving. It's really just a bunch of pictures, one right after the other, one every 30 seconds we actually would have, or now 60 seconds in some cases. And what would happen is this electron, this is a television, this is an old-fashioned television, and you see the electron beam is shooting these electrons here, see how it's shooting out? And there are these magnets all around here. An electron beam, actually, if you have a magnet for electrons, if you take a magnet, an electron beam, if you put the magnet, the beam will bend away, And so we put these magnets here, and when we put electricity in a magnet, it's called an electromagnet. The magnet actually gets stronger. And so we can actually use these magnets to move this beam around the screen. So that's how we would actually, and as the beam touched this phosphorus screen, it would emit, the phosphor would light up. And so it looks like one image, but what's really happening is there's a beam that's going across, all the way across like this. And then when it got to the bottom, it went back to the top again. And every time it went through the screen one time, that was called a frame or field. Back then, it depends on how you count. But so that was the cathode ray tube. This was an early TV transmitter here. This was in the Empire State Building in 1936. You can see it looks just about very old-fashioned. And this is a picture of our transmitter at FOX40 yesterday. You can see it's a lot smaller and a lot more modern looking. But believe it or not, on the inside, we're using basically the same technology still. We're using a much more advanced version of the tube to transmit. It's called a IOT, inductive output tube, but fundamentally the same thing. So how do we go from that to now? Well, of course, in the ensuing years, many additional technological developments led to greatly improved quality and reach of video broadcasts. However, none have transformed the field of broadcast engineering more than the semiconductor. Now, although the semiconductor has led to improved non-tube versions of TV cameras, displays, receivers, and transmitters, the computer has transformed the field of broadcast engineering fundamentally. It is no longer just tubes and radio waves. We still do that, but it's not all it is. Originally, broadcast engineering was a specialty of electrical engineering. However, it's now a multidisciplinary field, which means it's different kinds of things, encompassing computer science and IT in addition to electrical and RF engineering. As a side note, now tube transmitters, as I mentioned, although we have non-tube versions of all these things, and in fact tubes are kind of dying, we still use them for high-frequency, high-power television transmission, such as at our station. And we're just beginning to phase those out for semiconductor versions. Now, I want to show you to make my point clear about how computers have become an integral part of broadcast engineering. I'm going to show you a picture on the left here. This is a picture from the Empire State Building again in 1936, a television transmitter. And this is a picture of the master control room, which is basically the main control room at FOX40. Notice all the computer screens, all the computers everywhere. It's basically all computers. Here, not a single one. So it's really become quite different. So what do broadcast engineers do today? If you were going to be a broadcast engineer, what would you do? Well, broadcast engineers at TV and radio stations have always designed and maintained all the technology in the facility and outside of it. And we have quite a few sites outside of it to transmit or repeat our signals that keep the station on the air, allowing the station to continue to receive programming, generate content such as news, and to transmit that content both over the air as well as now to partnered distributors such as cable and satellite companies. Because we've gone outside of just transmitting over the air, now we send things to cable, satellite, even the internet. This was a picture of the satellite and microwave receiving equipment at our station. So all these little things in these racks, these are all used to receive signals from satellites or from live trucks. I don't know if you've ever seen a live truck. It's those, yeah, you've seen that. So we use those there. So broadcast engineers at stations are fundamentally, we plan and design when we have a project. So let's say the news department wants to put in a new fancy Neustron 2000 of some sort or other. We will plan and figure out how to do that. We'll design it. We'll figure out what we need to buy or what we need to change to make that happen. And then we install it. We put it all in. We wire it up. And then we maintain and troubleshoot it when it stops working, which it inevitably does. Because unlike consumer electronics, in your house, you have a few TVs, a couple of disc players, maybe not even today, you don't have those, and a Roku or a PlayStation or something. Well, at our station, we have hundreds and hundreds and hundreds of pieces of electronics, and inevitably, they die. Semiconductors don't last forever. Nothing does. And eventually, they have to be replaced. But unfortunately, a lot of times, because the system itself is so large, the first step is figure out what in this system is not working, right? You have to actually figure out what piece of equipment is not even working. All you might see is, well, the television, our station looks a little weird. Why? We have to figure out why. This is our transmitter. I want to show you a little about the transmitter. So this right here is one of two of our main transmitter vacuum tubes. This is not actually the vacuum tube itself. The tube's inside of this large canister. And by the way, to give you a sense of scale, this is about my height, this whole cabinet. So the vacuum tube is about this tall, and it's made of glass, but it's coated on the outside, so you can't see into it, unfortunately. But it's very high power. We put about 40,000 volts on the tube. This is the back side of the transmitter, the back side of what you were just looking at here. There's both of them there. This is a grounding wand, so when you want to work inside of it, there can be a charge in there. You don't want to die, so you have to make sure that the charge is grounded, because if there's a charge, electricity loves the earth. What do you think about that? So it's always trying to find a way to get to the earth. Earth is home. So you always want to ground it with the rod, so if there is a charge, it goes through the rod and to the ground, rather than through you to the ground, which you don't want. So, and then there's also an additional safety mechanism. So to actually open the door, do you see this? This is the handle actually opens the door to get into it. By design, if you flip this over, it's going to see it says short to earth. It will actually force most of the components just by opening the hinge. It'll force everything to ground, but we still have the grounding wand just to make sure. This is a picture of the outside. So here you can see the back of the transmitters. But once it comes out of the transmitter, we have to do some different things to the signal. One of them is we filter it to make sure it's within the band of frequency that we are allocated to transmit on. This large thing here is a filter. And basically, if there's any spurious emissions, we call them spurious emissions, and basically means anything outside the frequency that's not supposed to be there, that filter will basically get rid of them. And then up here, we have a dummy load, which is for if we need to operate the transmitter, but we don't want to go to the antenna. We can put all that energy into a dummy load, as it just basically dissipates as heat. So this is how we do that. This is the base of the tower. We call this a catwalk. And below, you can see these cables. That's actually the cable for the output of the transmitter after it goes through the filters and everything else. So it goes down that, and it eventually goes up the tower. And you can see here, our tower is about 2,000 feet tall. That's almost twice the height of the Sears Tower. And when it gets to the very top, it goes onto the antenna, and it goes all over the place from there. So I want to show you about the studio a little bit now. So we've talked about the transmitter at our facility, and you kind of see what kind of things you'd be working on. I want to show you what's at the studio, because in addition to transmitting, we also now, a lot of it, probably most of it, is making sure that everything we need to create the content is working properly. This right here is the actual audio mixing system we use. So you've all, especially if you're in this academy, you've all probably worked on an audio board. This is actually the engine of the board. So it's a series of blades. We call them blades. And each one on the back, you have an input for an audio input. And each of these cables, so some of these come from microphones, some of them come from video servers that we use to play out video. We want to hear the audio from it. And so all of them go into these blades. We also have some for outputs, for aux feeds, things like that. And they're all networked together with a computer network, so that all the blades can talk to each other and function as one cohesive mixer. So This is a router. We'll call this a video router. Basically, all of the video in this facility, at least much of it, goes into what's called a router. So every signal goes into this device, and there's lots of outputs from the router as well. So you can effectively mix and move signals around to different places as it's needed without having to physically move the cable around. So that's what the router is. And on the right here, we have what's called GPIO patches. So this is used basically to send basic on-off signals from different pieces of equipment to get the equipment to talk to each other. This is a rasterizer. I don't know if you've ever worked with a rasterizer, but basically it allows you to take a video signal. In this case, this is actually a camera in our control room. So you can actually see the video of the control room and look at different aspects of that signal. So this is a waveform monitor. We don't use it as much as we used to. It used to be much more important. But it still is important to some degree, because we want to make sure that we're not blasting and past the visible. So you want to make sure it's not too bright, basically. You want to make sure your details are not too bright and you're not missing any detail by making it too bright. You also want to make sure that you're not losing any detail from having it too dark. So 7.5 IRE is the level at the base. 7.5 IRE is a unit of brightness. So if this was a picture and not actually real life, you know, up here might be 50 IRE, and down here at this black thing, that might be like 10 IRE. And total black is 7.5. I don't know why it's not 0. In Japan, it's 0, but here it's 7.5. No one ever told me why. And then 100 up here. So you want to make sure that most of the things are right within the center here. And then you can see all this other stuff, and then it'll say, that doesn't look like, look, it goes way down to the negative. What's that all about? That's actually what's called the vertical blanking interval, and that's actually how the electricity tells the receiver, the television, that, hey, we're going to a new picture now. So this is one picture, and then this is basically how we tell the television we're going to the next picture now. So otherwise, the TV is dumb. It doesn't know how to get from one picture to the next. We got to tell it. This is actually a vector scope. This lets you see, visualize the colors on a graph. And you see how we have different colors here. We have blue, we have green, we have red, we have magenta. And you can actually visualize where the colors are. The reason we do that is we want to make sure, especially with human beings like anchors on camera, we want to make sure that they look just right. We want to make sure they don't look too green or too red. They're very, very unhappy when they look like a Smurf on TV. So not as important now as it used to be in the old analog days, but you want to make sure there's certain ways when you have a person on the air. You want to make sure it's pointed a particular way, and that's how you check. And if it doesn't look like it's going the right way, you adjust the color settings on the camera so it does. And this down here is audio, shows you different channels and levels of audio. So we don't have audio on this camera, so it's all blank. This is a production control room. So we have, in most television stations, we have 2 control rooms if they do news. If they don't do news, if it's just like ION, a channel like that, there's only probably 1, if any at all. But the production control room is where if you were the technical director, say, you would be sitting here and you would actually operate the equipment that would switch from one camera to the next, would put the graphics over the images, things like that. And then there was master control, and I showed you a picture of master control earlier when I was showing you the Empire State Building picture next to it. That master control is how we actually finalize the different sources and take it to air. So production control will create the news product and hand off the signal to master control. And master control will then take it to the transmitter as well as Comcast and all those other people. Master control would also be the ones to run commercial product, things like that. This is our studio. You can see the cameras, pedestals, chairs for the anchors, lighting up at top, all LED now. And this is actually the production control switcher. It's actually not the switcher per se, it's the control panel for it. But you see all the different buses on it. These are different colors. They have different buses. Basically, the buses allow you to layer your video. So when you watch news, you'll see the camera with the anchor, and then on top of them, you might see the what we call a lower third, where it tells you their name or whatever they're talking about. So that would be like the bottom bus would be the picture of the anchor, and then the bus above it was where we layer the graphic on top of them. And you can use this panel to do all of that. Now, nowadays, we have automation software that does a lot of that for us. But especially if you want to get into things like sports, you can't automate that. It's unpredictable. So you still have people hot punching things like that. So computers in broadcast are now used both directly in the air chain. The air chain is a word we use. It's a fancy word meaning the signal, how it flows. And also they support the creation of the content. In other words, they are used in situations like to automatically control different video servers according to a playlist. So you might have what we call a master control automation system. So you might have 3 computers, each one plays out video out of the back of it. You might have one that plays commercials, one that plays Judge Judy, and the automation computer will actually, basically we put a playlist in there, and that computer will tell these computers, hey, you played Judge Judy. Okay, let's wait 20 minutes for Judge Judy. Okay, you play that commercial from the lawyer guy, and then you play the commercial for the promotion for the news, and so on. Computers are also used in the newsroom to keep track of stories through a centralized system. And they can also gather weather or election data and automatically feed that data into video servers to then put that data into the video itself. So here's an example of ways that computers can be used in broadcast. So as I mentioned, so specifically computer science, including scripting and software development, have become an important part of broadcast engineering. This is done in stations, but also if you want to get into more the supportive side of the field, whether you want to work in an integration company, someone that basically puts things together for stations, or actually you even want to work in a place where you're making the equipment, or manufacturing and designing it, or the software for it, that's especially important as well. But we are seeing that a lot of stations very much value in-house development of software, some including mine. So as an example, we can look at one of the patents for an invention that I developed working as an engineer at FOX40. So this is a United States patent 9674464. This is for a news production system with DVE template features. So DVE stands for digital video effects. So this is a picture, these are some diagrams from one of the patents of an invention I made for elections. How do we get data from elections and put them on the air in the most efficient way possible? So in this system, we have 4 parts. And the election system on the bottom right is a computer, and that's actually the subject of the invention. But the election system gathers data from different sources, and it communicates to these other computers, these other 3, that are used in the station to create news content. The video source it might just be an image of the anchor talking. And then the DVE system is digital video effects. That's what actually takes a graphic and keys it on top of the image. So in this case, you can see we have an example where we've put a slide on top of the video. So it says U.S. Senator, California, and we have the percentages of who's winning. We put that over it. And then we have a scheduling system on the bottom left. The scheduling system is used, as I mentioned, there's like a playlist, and a computer will tell this computer, do that, do that, do that. And it goes according to like playlists. This is just like something you'd see in iTunes almost. It's a little bit more complicated, but essentially we go from one to the next to the next. It says story A, then story B, and at different stories, we tell this system, the graphics DVE system, to key different graphics over the story. In the election system, essentially it feeds the election data to the DVE system, but also, and this is an important part of the patent, the election system also tells the scheduling system to modify the schedule based on how hot races are doing. So if a race is very close, this election system might tell the scheduling system, hey, move this one up. This is important. People really care about this one. And we can do all that now with this invention without the need for human intervention. So it basically, if any of you have ever seen a newsroom, it's a very hectic place, especially on election night, and a lot of things can slip through the cracks. So it's not about replacing people as much as it is just making sure that things don't get left behind. And so that gives you an idea of how important computers are nowadays. Now, what's the future of all of this, the future of broadcast? Well, we have something called Next-Gen TV, which is more technically called ATSC 3. It's the next digital standard for television broadcasting over the air. It's designed for direct reception by mobile devices as well as conventional TV sets. So the idea is that at some point the iPhone, the Androids will actually be able to pick up these TV channels directly without any other intervention. You're not using your data plan, you're just coming right off the tower. And it'll operate using IP, which is like the internet technology, over the air, and it'll include personalization and interactivity. So if you see something on there, or it might even change the video based on your preferences. There does exist some debate as to whether over-the-air television broadcasting, even with this new standard, will remain in the long term at all. And that's a good debate to have. But it doesn't mean that broadcast engineering is going away. That's the kind of the case I want to make here, and make sure you all go home. The take-home point is, even if there's no more over-the-air, broadcast engineering is still staying around. The reason being that there's always exciting new internet-based methods of delivering television from the local station, such as something that we're just rolling out now called OTT. That stands for over the top. And basically that means, we might be delivering things through ways other than over the air. And while all the things I've showed you are important and are a very important part of the legacy of broadcasting, computers have become just as big a part now. And I don't really foresee television or radio ever going away. I think there's a lot of talk about that in the media sometimes. But the bottom line is, people still want their local news. They still want sports. And those are things you can't really deliver on YouTube or Facebook. People are always going to want journalism. And they always want to see what's going on. They don't want to hear, they don't want to just read it in the papers. They don't want to see it through what someone said on Twitter. So, the field is very much alive. Yes, sir? Did you go to college? Yes, I went to Michigan State University. I have a bachelor's degree in television production, actually, not engineering. But when I was doing that, and why did I get into production? It was basically I was in high school, and at senior year I took a class in film studies. And we had to do video editing in that class. We actually had to recreate a scene from a pre-1980s movie. I picked The Exorcist. We did the pea soup scene where the girl spews. It's a lot of fun to do. We had to clean up a classroom when we were done shooting it thoroughly. And I got to do the editing for it, and I thought it was a lot of fun. And so went to college, got a bachelor's in production, and then I thought, this technical stuff is really cool. So I actually went to an associate's program that's certified by the Society of Broadcast Engineers in Milwaukee, actually. And I got associates in electronic communications with a specialty in broadcast, which is basically associates in broadcast engineering. And then out of there, I got hired by FOX40 here in beautiful California. I've been here ever since. Mm-hmm. So if anyone, if you're interested in broadcast engineering, have any questions, a really good resource is the Society of Broadcast Engineers. They do have a youth program as well. They kind of reach out to people in middle and high school, as well as college. They have a youth membership as well. So they're a very good resource for getting an idea of what the industry involves as well as where it's headed. If you're interested in radio, if any of the things I talked about in the first half of this look really interesting to you and you go, I'd love to play with that stuff. There's a lot of adults in this country that love to play with that stuff. They're called hams. And it's actually it can be a lot of fun. Ham radio, you've heard, it's called ham. It's amateur radio. And they basically go around and play with radio. And they do a lot of serious things as well. They help the law enforcement sometimes. They'll help in natural disasters. They have particular bands of frequencies that are allocated to that. So what you can do is you can actually go to the FCC, you can take a test, you just basically study for it, and then they'll give you a license, and you're now a licensed amateur operator, and you have certain frequencies you're allowed to dabble in, and you can basically build your own radio, or you can buy a radio, and you can talk to other people as well. So if any of that interested you, that's an avenue you can pursue. All right, thank you very much.